Okay, here I have a few examples of the problems that you might see in the ISAT. Well, these are actual sample problems taken from the ISAT, so I'm going to go through these together with you. And we've been working on defining, one of the sample areas we've been working on is defining functions. So we have here, it says the outside temperature in degrees Celsius. I'm going to grab this highlighter here. So it's in degrees Celsius, and we're talking about the temperature, and it's right over here, right? So that's our temperature in degrees Celsius is modeled as a function of time. Time is a different thing, right? So time, so we're saying that how the temperature outside depends on what time it is. It's a function of time. So they want us to look at this graph and answer a question or two. So let's take a look. So it says, I'm going to zoom in here a little bit. Find the average rate of change in temperature measured as degrees Celsius per hour. So I'm going to do my Celsius per, I always think of that axis as telling me the origin per hour. This is my change in Y, Celsius temperature, right, per change in X, right? So rise over run. So they're actually just asking me for the slope. When it says average rate of change, that's a slope question. And we just need to know rise over run. They're specifically asking about between 7:30 and 9:30. So what that means is I can ignore a lot of the time here. I've got to start by being smart and understanding where 7:30 is. So this is 7 right here. And this is 8. So halfway is right here. So that would be 7:30, right? And I guess that would make this, hold on, 7:30. So I guess that would make this number 7:15 and this number 7:45. These are quarter hours, right? So that would make 9:30 right here, halfway between 9 and 10, right, is 9:30. So here's 9:30. So 9:30 is halfway. So they're saying between this point and this point, what is the average rate of change? And the average is really nice because the rate of change is changing this whole time. We have a curve. So there isn't a single one. But if I think about, how would I connect these 2 points? I can figure out a rise this direction over a run this direction. Okay, what is this? This is 2 hours, right? And this would be what? From 1 up to 7, so it went up 7 degrees. So how do I write that as, as a ratio? The average rate of change is, so I guess I better say 7 over 2. Which is 3.5. Well, the problem says enter your answer to the nearest whole number. So the nearest whole number from 3.5 is 4. However, I'm going to zoom in a little bit closer. Okay, this looks to me like this is really at 1. However, let's look even closer here at this part of this graph, because to me this looks like it's just under the 7. At this time, right here, it is not at 7, it is a little less than 7. So therefore, this is not a rise of, ooh, and I wrote 7. Whoa, Mr. T, woo. Hold on a minute. This isn't 7. The total is 7, but the distance between 1 and 7. We have to read that. Oh my gosh, how embarrassing is this, right? It is not 7. Okay? This is why the slope formula is y minus y. You might remember this. Y minus y over x minus x. And it's to help guys like me who make big mistakes, because this is 7 for sure, but this is 1. And so the growth or the rise is only 6. 7 minus 1. Just like this 2 came from taking 930, delta, this is the change in time, 930 minus 730. Oof, writing really poorly here. But that's how we figured this is 2 hours that have gone by. 2 hours. So then we have to do the same thing. It was 1 degree and now it's 7 degrees, so it's risen 6. So going back to my answer here, it's 6 over 2, which equals 3, not 3.5. So when it asks for my, and it's not going to be 4, so when it asks for my nearest whole number, which is I think what it asks for over here, 3, even though this is maybe a little under 7 and a little under a rise of 6, but almost total 6, you know, if this was 5.999, it's going to round to closest to 3. So 3 is the number I'm going to go with. Man, that was a close call, but I'm glad I made that mistake because it helped me take a minute and remind you about our slopes. Where do we get them from? Rates of change, where do they come from? Rise over run. Now that doesn't work with a curved line. It only works with a straight line. So it only works when they're asking for an average. If they're looking for an instantaneous rate of change, well, they won't on this, but on the SAT they might, because that is a calculus problem. Right? Trying to find instantaneous rates of change, that's something we do in calculus class. All right, here we go. Not what you'll need to worry about. We have another function here, and now we're going to go through, let me highlight, let me get some colors in here we can use. So this time, something is a function of time, so we still have time down here in years, but we have a different function, and it is the population of the town as a function. So the population depends, the population of the town depends on the time, and that's the whole thing that makes it a function, is there's a dependence. So the time population is not one fixed number, it's changing, and what the population is depends on when you look. Okay? All right, so it says the population is increasing throughout the time period. We have to answer, it says, determine whether each statement is true according to the graph. Select true or false for each statement. You know what I'm going to do? I'm going to move it over here. Now I'm going to move it over here. Boom. So we have to figure out whether or not this statement is true throughout this graph. So is it increasing throughout the entire interval? The only thing I don't know is that is almost a flat line. But so that is a really tricky thing. It looks like it's curving up between 0 and 2.5. It did go up a little, very little. I don't think it was flat. But if they want that to mean flat, well, then we'd have to say, yeah, it was decreasing or not increasing. But I think this is increasing just a little bit. So my answer would be true. The population is increasing. So all we're really looking for is the line going up. And even if it starts to flatten, but it's not all the way flat, it's still increasing. I would mark that one true. That's how I'd mark it. I might get it wrong though, because again, if they said this is flat, then that is not an increase, right? Anything going down would be a decrease, and anything flat would be constant, not increasing. Okay, next thing says the greatest growth in population was from year 5 to 15. So here is 5, started out at 10,000, and by year 15, it was at 15,000. And man, that really looks like the greatest growth. I think it is. And what I'm going by how steep it is. And I can see after this, it starts to taper off. The growth is not as great, right? Before it's kind of flat for a while, and then it just barely starts to tick up. But between 5 and 15 years, man, that line is near the steepest that it's going to be. I can tell also when I look really closely here, it looks like it's still bending upward at the beginning, which means it's flatter on this side. And it begins bending downward here, which means it's flatter on that side. But the steepest area is in here. So when it says the greatest growth in population was from year 5 to 15, oops. When it says that, I think that's true. I think that was the greatest growth in population because that is the steepest part of the line. It says the population has a constant rate of change. I'm going to disagree with that. A constant rate of change would be linear. And that would mean that you would see the line be a straight, flat line. I don't see that being the case. This does not look linear to me, so I would say false. Because this is a curved line, so I would call this nonlinear. Nonlinear means it does not have a constant rate of change. It's not, in other words, this line isn't straight, always going the same way. It's kind of slower, then it starts to get fast, then it starts to slow again. So it is not constantly changing the same. It is changing how quickly it's changing. It's changing the rate of change. Okay, and then lastly, the population was about 9,000 when the town was founded. So what I got to do is I got to figure out, was it about 9,000 when the town was founded? Well, I'm thinking the time was founded at 0. So the only thing they're really asking me is this about 9,000 here. I think it could be, but to be sure, this is going to be 5,000. The difference between this line here and this line here is 5,000. So the middle point right here, that's 7,500. So that would mean this is probably 7,000. 9,000, I don't know. I don't. Let's see, you have 1 interval, 2 interval, 3 intervals for 5,000. So this is a third of the way to 5,000, which is 1667. This is another 1667, which is 82 something plus some. I think that that's a good guess. It's an estimate, so I'm going to say yes to that. True. Okay, now that's just an estimate. You're trying to estimate, is that about 9,000? And you probably don't even have to get as technical as I did there, but that's what you're looking at with that problem. Okay, we have another problem. Boom. Share of one value. Let me make that just a little bit smaller so we can zoom in a little bit more. Try that again. Okay, the share of one value of stock over 15 business days is shown on the graph. Oh man, so this is one of those non-linear rates of change, right? It's curving, it's not linear, right? So this, where the value of one share, that is one measure, is a function, again, of time, how many days it's been. So the value of the share is a function of the days. So how much the cost for one share, how much one share was worth, depends on what day you checked, right? That's what that's saying. That's why it's a function. Okay? So now they want to know, what is the rate of change in the value of one share of the company's stock in dollars per day from day 0 to day 15. So we're going to start at day 0. So we'll mark that. Day 0, the value was 5. And again, if they're asking rate of change, they're just asking you for the slope. So started out at 5, day 15, these are counting in 2, 0, 1, 2, 3, 4. So this would be 12, 13, 14, 15. So it started at 5. Where did it end up? At 11. So we have here a slope that we can estimate over that time period, looking at rise over run, okay, from 5 to 11. What is this slope? Well, it's 11 minus 5. So my rise was equal to 6. And my run was from 0 to 15. So 15 minus 0. So it went up $6 over 15 days. Okay, now I can use my calculator, and when I do, I'm going to find this is equal to 3/5, which is 0.60, same thing as 60 cents. Okay, so the rate of change in dollars per day is $0.60 per day. It went up $3 every 5 days. Okay. Is that right? Wait a minute. No. Look, I made a mistake again, Mr. T. I didn't use my calculator. I used my head. This is 5 times 3, or 3 times 5. Ooh, this is so good because I can come in here and show you how you reduce, right? So this is 3 times 5, and 6 is 3 times 2, right? So the 3's are going to cancel, all right? Which means I'm left with not 3 over 5, but 2 over 5. 2 over 5 reduces to 0.4. So look, you don't want to be like me and make this mistake. Use your calculator, put 6 divided by 15, get 0.4, and that's how many dollars per day. It's going to be 40 cents per day, but they're not asking you for cents. So you wouldn't put in 40. You'd put in $0.4. $0.4. And if you want to add a 0 here for 40 cents, you can show that. That's fine. But it went up 40 cents each day over the course of 15 days, which was a total of $6. Okay. Whew. Okay, we got one more problem here. Okay, so Jared is measuring the total height of the water in a bucket at different times, and they're displaying this in a graph. So what we have here is we have the time down here below, and we have the amount of water in the bucket over here on the side. So can we say how much water is in the bucket depends on when we look? If so, then we have a function, and it looks like we do. Okay, so how much water is in the bucket depends on how much time has gone by. Now we need to look at this and we need to figure out of all these statements here, how many of these are true. Let me shrink this down and move it closer. And then we can zoom in here. Okay, so it says the height of the water in the bucket increases 1/2 inch every minute. Woo! Well, what would that mean? In 10 minutes, what would that be? So if it's 0.5 is 1/2 for 1 minute, it would be 5 inches every 10 minutes. So I don't think it's going up 1/2 inch every minute. I think it's going up 1/2 inch. So here, look closely now to see if you can figure this one out. Here it's at 1. 10 minutes later, it's at 1.5. So it did increase 1/2 inch, but not every minute. It was 1/2 inch every 10 minutes. So I'm not going to select this one. Then it says the height of the water in the bucket increases at a rate of 3 inches per hour. Okay, well, here's the beginning. Here is 1 hour, 60 minutes. There are 60 minutes in an hour. So did it go up 3 inches? 1, 2, 3, yes. So this one I like, and I would definitely select B. It is increasing at a rate of 3 inches per hour. In the first 20 minutes, the height of the water increased by 2 inches. So let's pick a different color here. And let's just go the first 20 minutes, which is just until here. Okay. Did it go up 2 inches? It is now at 2 inches, but it started out at 1. So it really only went up 1 inch. So me no like it, that one. I would cross that one out because I don't think it increased by 2. It increased to 2 from 1, but that was an increase of only 1 inch. It only went up 1 inch. Next, it takes 60 minutes for the height of the water to increase by 4 inches. And that is another one where, man, they're going to throw kids off and their language skills is what's hurting them, not anything else. Because this is misleading if you don't understand increase by versus increase to. If I was looking at the word, hey, it's increasing to 4 inches, well, that would mean it increased until it got to the number 4. So that would be true. But in 60 minutes, it didn't increase by 4 inches. When we write the word by, that's talking about how much change there was from this to this, which is a change of 3 inches, not an increase by 4 inches, but an increase by 3 inches. Or another word we would often use is increase of 3 inches. It's another way to write it. But then we would say an increase of 3 inches. Okay? So when we say take 60 minutes for the height of the water to increase by 4 inches, that's false. If it said it takes 60 minutes for the height of the water to increase by 3 inches, that would be true because it is increasing by 3 inches. Anyway, we don't like that. And man, I hate the word play because to be honest with you, you can read this graph, but if you don't understand this word play in here, the height of the water to increase by, you're going to probably think, oh yeah, look, it is up to 4. And it's not, it's just not asking that. It's asking how much did it increase by? What amount did it increase by? Okay, what was the amount of increase? Okay, here it says, after the bucket has been outside for only 1 minute, there's no water in the bucket. Well, that's false, right? Because I can tell that's false because if I look right here, okay, let's go with a green color here. Look where it started. Even at 0 minutes, there was already 1 inch of water in the bucket. So after the bucket was outside for only 1 minute, there's no water in it. False. There was already water in it. It didn't go away. It just started filling up more. And then lastly, I do like this last question because it says, there is already 1 inch of water in the bucket when Jared places it outside. So I'm looking at time zeros when he put it outside. There was already 1 inch. So I like this one. So the two I like, for me, I would say yes. Oops. I would say yes to B and F on that question. I think those are the 4 that I wanted to get through with you today. 1, 2, 3, 4. Okay?